join us. I'm kind of worried. Okay, so thanks for coming this morning. So maybe I mute you off, okay? Because otherwise we are recording this. Okay, so let's very quickly review what we learned last week. So we said the ultimate goal for sintering is trying to use the lowest possible temperature to get the highest possible density, right? So that's the ultimate goal. And there's two routes. So route 1 is densification. Route 2 is coarsening. Okay, so this week we're going to learn how can we control our process in order to have route 1 or route 2. And also there's a two sintering. So there's a solid sintering and liquid sintering. And also we learned this Yang-Subs equation and the Kelvin equation, because these two equations is very important to tell you where will this atom go. Okay, so the mechanism behind it is the atom will always go to the lower NH place. Okay, some people call lower NH site. Okay, so no matter what, if you can overall reduce the total NH, so you are going to go forward. Okay, and from this Yang-Subs equation and Kelvin equation, so we already proved that the free energy of one atom is actually higher than the flat surface. Okay, so that's why actually the atom is going to move from the convex to the flat. Okay, and for the concave, it's a little bit complicated, but just remember this moment. Okay, so concave is a case where R actually is less than 0. Okay, so delta mu is actually less than 0. So this side is actually the lowest NH site. Okay, lowest NH site. So in principle, so the atom will move from the mountain to the land to the valley. Okay, so that is what we learned so far from last week. So starting from this week, we will examine more details. So how can we use all these things we learned last week and learn how to control whether we can move to more route 1 or route 2. Okay, and also before I move on, so just explain the CA2 next week. Okay, anyway, I'm going to give you a math tutorial next Tuesday, 5 p.m. Right, I've sent email already. Okay, 5 p.m. Okay, next Tuesday. Okay, I'm going to give you a math tutorial. Okay, so very quickly, I'm going to help you to narrow down what is examinable. Okay, so please join this one. The link is the same. Okay, for 3011, there's only one link applies to everything. Okay, online. Okay, so this is next Friday. Can you mark your calendar? 5 p.m. So I'm going to narrow down, as I said, what we have learned. Okay, and CA2 is covered from week 1 to week 3. Okay, so altogether there will be 33 points. Okay, 33 points. Okay, so CA2, and also the question is very similar to the tutorial questions. Okay, so make sure you know how to do all these tutorial questions. Okay, the CA2 is structured questions, structured short answer questions. Okay, very similar to the tutorial. And also CA2 is 9, so it will be 33 points, and CA3, okay, so we have Prof. Eugene part, which is 17 points. Okay, and my parts also 17 points. So since we have already tested you week 1 to week 3 in CA2, so in week 3, in CA3, so this portion, I'm only going to test you the week 4 and 5. Which means whatever has been tested in CA2 won't be tested anymore in CA3. Okay, and also because school's new rule is you cannot have MC to skip any quizzes, because all these quizzes have very high weightage, so you cannot just simply say here I have MC, so I can use other parts to proportionally calculate the total marks. This is not allowed anymore. Okay, so please make sure you attend all the CAs, okay, because otherwise in week 13, you have many more quizzes of all the other courses come together. I'm very sure you will have a lot burden there, a lot of pressure there. So trying to clear this part by next Friday. Is it clear? Try your very best to clear this part by next Friday, because this part won't be tested again in CA3. Okay, as for the Eugene's part, for Prof. Yu's part, the 17 points, please consult with him whether this is going, what the examination level range is going to test you. So please just email him directly. Okay, so for my part, CA3, only week 4 and 5. CA2 is week 1, 2, 3. Okay. Taking up. Oh, sorry. Yeah, Raju, I got confused because I'm teaching 2 courses. Yes, Raju, Prof. Raju. Okay. Yeah, thank you, Prof. Raju. Okay. So metal part, please ask Prof. Raju. So for my part, so the final words are my parts. Okay. CA2 cover week 1 to 3, which is until what we taught today, and CA3 is only last 2 weeks, week 4 and 5. Okay. Thank you. Too many courses. And also, I still have a PG class, the postgraduate course. Okay, so it's pretty also crazy busy. Okay, but anyway, so so as I said, I'm trying very much to reduce the burden. And since I understand in week 13 there's too many quizzes, so at least for my part, I try to only test you 2 weeks. Okay, week 4 and 5. Okay, and for the and also mark this date, next Tuesday, there will be a math tutorial trying to reduce the examinationable range. Okay, so thank you. Take care, everyone. Okay, I know it's difficult for all of you. Okay, so this part, as I said, this week is very difficult, but according to my past experience, after this hour of teaching, together with the tutorial, 95% students will understand the concept. Okay, so no worry. So even you have big doubts here and there, so let's try to clear everything by the tutorials. Okay, so no worry. And also we will have an extra math tutorial to help you. And I'm going to give you a big consultation and also trying to narrow down what is going to be examinable. Okay, so let's move on. So we learned this one. This is a Kelvin equation, right? So we learned this Kelvin equation. Okay, so okay, anyway, here we're actually sharing with you some very common practice in material science. Okay, so like because we know that P curve is actually very close to P flat. So is it true? So if you remember, we go back to what we calculated last week, right, in the tutorial. Okay, so you know that you can say this is P naught, which means you don't have any shape. No shape, right? And this is with the shape, which means if your particle, if this one is 90 nanometer, this one is 900 nanometer. So you can see actually, so they're very close. So P naught is 17.535. Actually, if the particle size is like 900 nanometers, so it's 17.555. Okay, so we can, this is a very valid assumption. In material science, there's a lot of assumption there, okay? So the assumption is if the P curve are very close to be flat, so this delta P is actually, we can convert, we can get rid of this norm. Okay, as most material scientists, we don't like the norm. So how can we get rid of this norm? So in the end, we can get this is a final answer. So which means norm P curve over P flat is equals to delta P over P flat. So how can we get so? So there's a small math manipulation there. I just very quickly help you to go through. If you have problem, no worry. I'm going to explain again in the tutorial. Okay, so norm 1 plus x equals to x minus x squared over 2, x cubed over 3, x power 4 over 4. Okay, so this is the mathematic equations which is available everywhere. Okay, so we starting from this equation, I'm giving you the special case now. So if the x is very close to 0, for example, so now let's say if I give you an example, if x is 0.1, so tell me what is norm 1.1? Don't use calculator. Can you just quickly give me an answer? If x is equals to 0.1, x equals to 0.1, so which means now I'm asking you norm 1.1 equals to what? A very, very quick one. Can someone give me a very, very quick one? Jay? Farah? Lida? Malkan? Norton? Sean? Everyone? Can you quickly give me an answer? I mean, give me an approximate answer. I saw one Correct answer. Very good. Very good. Okay. So for example, let's say this one is 0.1, right? So that means this one equals to a norm 1.1 equals to 0.1, right? So this portion is 0.1, okay? Minus, this is 0.1 times 0.1. So you're going to have 0.005, correct, right? So then this one will be even more, 0.00033. This is even bigger. So that's what we call is higher order. So in mathematics, normally this, if the x is very, very small, right? So all this higher order actually can be ignored. This is also, again, a very valid assumption because you can see compared with 0.1, the 0.0005 is much, much, much smaller. The magnitude is much, much smaller. Okay, so that is why, so actually if x is very close to 0, so we can see that norm 1 plus x is going to equals to x. Okay, equals to x. Okay, so we can ignore the higher order. Okay, so so far, okay, all right. Okay, good, good. I saw a correct answer. Thank you. Okay, so continue. So which means since x is very close to 0, which means 1 plus x is very close to 1, right? So let's continue. Okay, so next, for example, if a is very close to b, so now I'm asking you if a is very close to b, so how about norm a over b? Norm a over b. Norm a over b. Why there's a noise somewhere? Okay, sorry. Okay, my question here is, so if norm a over b equals to, okay, norm a over b, if a is very close to b, so what can you do? What can you do in this case? So since we already said, if x is very close to 0, so this 1 plus x is actually very close to what? 1 plus x very close to 1, right? 1 plus x is very close to 1, okay? And also if a over a very close to b, which means a over b is again very close to what? Can you type? If a is very close to b, so a over b is very close to what? Yeah, thank you, Yongjin. Thank you. Yeah, okay, it's very close to 1. So which means actually this 2 is more or less like you can try to make this a over b is equals to something 1 plus x, correct? Correct, right? So that's what we put here. So we said, so this x actually, so you can change to 1 plus x, 1 plus x. Okay, so a over b, so a over b is equals to a plus something, a plus something, a plus something, a plus what? Which is b, right? You can put a b here, okay? And also if you put a minus b here, right? Can you do a math manipulation here quickly? So is this 2 equals to each other? A over b equals to 1 plus a minus b over b, correct? Yes or no? Can you type? A over b equals to 1 plus a minus b over b. This is very simple, the math here, right? Correct, right? Okay, thank you. Thank you. Okay, so which means a over b, I just do a very small manipulation. I take out 1 here because I know I need something which is x here, right? So actually then this a minus b over b is actually equals to the x. Is it correct? Right. So this is just a very straightforward one. So this one, a over b equals to a minus b over b plus 1. Okay, so then we also know that since a is very close to b, which means a minus b over b, this one is very close to what? This portion is equals to what? A minus b over b, which is supposed to be very close to what? If a is very close to b. Excellent. Thank you, Sean. Thank you, Yongjin. Thank you, everyone. Okay, which means a over b is going to be very close to b, to 0. So which means it's more or less like an x here. Okay, so then we can quickly have norm a over b is going to equals to a minus b over b. Are you following me? Okay, if you have problem, no worry. So in the tutorial, I'm going to explain again, okay, because this is a very common practice for material scientists to do the math manipulation here. Okay, so let's continue. This is conclusion already, right? So of course, the condition is what? Tell me the condition. When will this one be valid? Tell me, when will this one be valid? What is the condition here? norm A over B is going to be very close to A minus B over B if what? Tell me, what is the condition? Thank you, Lida. Thank you, Jay. Very good, very good. If A is very close to B, right? So the condition is here. The condition is if A very close to B, so A minus B is going to be very close to norm A over B is going to be very close to A minus B over B. Okay, so that helps us because what we say here, okay, right? Norm A over B. So for example, if I put P curve as A, P flat as B, is it correct? Because we just said A is very close to B, right? Because according to our calculation, actually the P curve is very close to P flat. Mathematically, it is very close. Okay, so we just simply take this P curve as A and the P flat as B. Okay, and also then we will get the upper one is A minus B. So A minus B, which is P curve minus P flat, which is equals to delta P. Okay, so delta B, so then it's roughly, we just keep the right hand side the same. We just do a little bit of the left hand side, get rid of this norm. So this is a very common practice for material scientists. Okay, so again, so this is our final conclusion here, which is P curve is going to equals to P flat 1 plus, this is atomic volume, this is surface tension, constant, everything is constant, and again, it is R here. Again, you can see this R, it is the P curve, which means once you have a curvature here, for example, like a balloon case, inside is P curve, outside is P flat, right? You don't have any shape constraint, please amplify, okay? So again, this one is inversely proportional R, right? Because it's 1 over R, right? So actually, no matter how I do the manipulation, the conclusion is still super simple. So don't be nervous by all this math manipulation. Remember the conclusion. The conclusion is P curve is actually again inversely proportional to R. Okay, same as Young's equation we learned before, same as what we have derived from the Kelvin equation. Yes, norm 1 plus x. No, wrong. Norm 1 plus x is not equals to norm 1, norm x. No, it's here. It's here, okay? So if you have problem to follow, I know there's something maybe you have problem to follow, but I will explain again in the tutorials. Okay, so this is the one. Norm 1 plus x. We need to get rid of norm. You won't see in the end you still have a norm somewhere. No, we need to use these equations to get rid of norm because norm is difficult to calculate in any modeling. Okay, we won't get rid of it. You understand, Yongjin? Okay, understand that. Good question. Okay. So I'll continue. Okay, so now this one is again is very close what we have derived before. It's the same thing. Very conclusion, same as Young's equation and the Kelvin equation. Okay, so let's further on. So there's another concept. Okay, this concept is a bit different. I think you have learned in your year 1 course, but let me just trying to emphasize again. Okay, so there's another concept which we call a concentration vacancies, because in the materials you always have vacancies. Okay, so the vacancy, one of the very fundamental things, vacancy is also going to move. Right? Vacancy is also going to move. Vacancy, like pores, is also going to move. So vacancy is moving from where to where? So maybe I give you a conclusion just in case you forget what you have learned before. Vacancy is going to move from higher concentration to lower concentration. Can you write down first? Vacancy is going to move from higher concentration to lower concentration. Can you write down first? Okay, you're supposed to learn this in year 1, but just in case, so I give you the conclusion first. Okay, vacancies move from high concentration to low concentration. So now let's see the vacancy concentration, since we already know how the vacancy is going to move, right? High to low R. Okay, so the vacancy, the equilibrium concentration of vacancy, we say no. Say no is have shape or no shape. Tell me. Say no is you have a shape, you have a radius or no. Tell me. Anytime if you see a say no, some people could say no. Okay, which means there's no shape or no shape. Okay, so this one, K prime exponential, this is enthalpy, and the KT, right? So you can see everything is constant, 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 constant. Okay, signal is a constant. So now, for example, so if I have a curvature here, and also this signal is a flat one, which means you don't have any curvature, or you can say the I is equals to infinity, doesn't matter, okay? So for example, now, if I want to create a vacancy here, okay? So compare with here. So do you think which part is more difficult to create a vacancy? Maybe at this moment it's a difficult question, okay? So you can imagine, right? Here, first of all, so this side A and B, which side have higher free energy, tell me? Vacancy means what? Vacancy means your atom need to move away, right? So do you think it's easier to move away atom in A or B, compared with B? Which side is easier to remove an atom away to form a vacancy, A or B? Okay, if this question is difficult, so let's answer the next question. So which side have higher free energy, A or B? A or B? Which side have higher free energy? Okay, A, good. This one you're comfortable, right? A have high free energy, right? So now since A have higher free energy, so do you think it's easier to overcome this free energy to become a vacancy? You need to overcome more free energy to become a vacancy or less free energy to become a vacancy? Tell me. If A, compare A, okay? So if your vacancy produced at A place, okay. If it's A case, A and B, okay. So which side you need to overcome more free energy to become a vacancy, A or B? Since everyone agrees that A have higher free energy, right? So now if you want to take out this material, take out this A, become a vacancy, obviously you need to times up this delta mu, right? You need to add up this delta mu, okay? Which means you need to overcome extra free energy to become a vacancy. Am I correct? It's just constant. All these are constant. Constant, no worry. As I said, almost everything is constant, okay? So delta mu, so now you can see in the one, if without any radius, the signal is everything is constant. You need to overcome this amount of the energy to become a vacancy. But now if you stand at a curvature now, so you have to add up, you can say add up delta mu, because you need, if you are, for example, if you're in the convex case, so you need overcome more energy to become a vacancies. So you need to add up this delta mu, okay? So this is the equations here. So then we do a bit of manipulation here. So since this is one of the tutorial questions, we don't have much time to explain the details here. So I'm going to explain more, but the concept is this one. Concept is, if you want somewhere to become a vacancy, you have to overcome the energy to become a vacancy, right? But once you have a curvature now, so the curvature automatically, once you form a curvature, you need to overcome extra energy, which is this delta mu to become a vacancy. So you have to times this, you have to add up this delta mu. So then the rest is just mass manipulation. And again, this mass manipulation is definitely not easy. It is very difficult. Okay, if you can do, wow, you are really, 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 really very good. Okay, but no worry, we will explain again in the tutorials, okay? So the question, okay, so this is the conclusion here. So C curve actually now is equals to C naught 1 minus 2. They all this constant. Same. If you compare what we have derived before, so the P curve actually is P flat, but the only difference here you can see is this is 1 plus, this is 1 minus. So what does this mean? So now let's recap. Okay, so for if you have a convex or concave, I think the concave you always have problem at this moment, no worry. So let me ask you this question. So for the convex and the land, which one have higher pressure? Convex and the land, the flat one, flat surface land. Which one you have higher pressure? Tell me. Higher pressure. I'm talking about pressure. Which one have higher pressure? Yongjin, Lida, Odella. Correct. Thank you, Sean. Thank you, Lida. Yeah, convex, right? Pressure actually is higher at the convex compared with land, compared with concave. But we derive this equation. You can see now we change the sign from positive to negative now. So obviously everything have to be changed, have to be opposite now. So for example, for R here, because for the convex, right? So the R is actually larger than 0, right? R is larger than 0. Am I correct? So no matter what, since this R is larger than 0, so this C curve is always supposed to be larger than C naught or less than C naught. Larger or smaller. Can you type? If the R is larger than 0. If R is larger than 0, C curve is supposed to be larger than C naught or less than C naught. Yongjin, can you think again? Because what I'm talking about, if R is larger than 0, R is larger than 0, which means the balloon case, you always use balloon to imagine, okay? Radius is larger than 0, which is convex case, okay? So if R is larger than 0, so the C curve is larger than 0 or lower than the C naught. Sherry, Sean, so Yongjin, how's your answer? Yes, okay, because this is larger than 0, so C curve actually is supposed to be less than C naught, right? So now I'm asking you, so where the vacancy move from the flat to the convex or from the convex to the flat? Yeah, thank you, Yongjin, correct. Yeah, less than C naught. So my question is, where the vacancy move from the left? Please be really patient with me. I know this at the very beginning you saw it's very difficult. As I said, after 2 hours of lecture and 1 hour of tutorial, I'm very sure 95% of you will understand fully. Okay, no worry. Okay, so follow me. Follow me. So now I'm asking you the question: will vacancy move from the land to the convex, or from the convex to the land? So we said before, you write down already, vacancy is going to move from where to where? From higher vacancy concentration to lower vacancy concentration, right? Lida said flat to convex. Lida said flat to convex. Is it true? Lida said from the flat to the convex. Correct, right? Because we said before, what we said before, so the vacancy is going to move from the higher vacancy concentration to the lower vacancy concentration, correct? So since we just already said that if this R is larger than 0, R is larger than 0, which means your C curve actually is less than C naught, correct, right? Less than C naught, okay? So which means this is flat, this is convex. So which means your vacancy is actually going to move from the flat, from the land surface to the convex. So Lida, you're correct. You're correct. Very good. Very good. Okay. Okay. So how can we understand this one? So anyway, so this is tutorial question next week. So let's derive this vacancy concentration equations showing at this one. I mean, if you can really do this one, you are really, really good. Okay. Really, really good. Okay. So no worry. So just recap. Okay, so as we said before, P curve is equals to P flat 1 plus 2 omega gamma KTT. This I is here, and also the is plus here. So that's what we said. So this P curve, because if it's R is larger than 0, which P curve is going to have the highest pressure, right? So your atoms is actually going from the highest pressure to the lowest pressure, so which is going this way. R larger than 0, delta mu also larger than 0. R infinite, so delta mu is equals to 0. If R less than 0, delta mu is less than 0. So the atom is moved this way. So now we have new things here now. The C curve is actually equals to C naught 1 minus 1 minus. So you can see R is still here, but the sign changed. The sign changed. Okay, so then where will this the vacancy go? Where will this vacancy go? So you think it's going to from the convex to the concave, or from the concave to the convex? Okay, simple. Is it going to be the opposite as the atom, or is the same as the atom? Can you just type same as the atom or opposite as the atom? I'm waiting for more answers. Thank you so much. Thank you so much. Yeah, very good. Kaijiang, Kuai Hua, Shang, Ryan, excellent, excellent. Your vacancy is going to move to the opposite direction. Okay, so these are the conclusions. As I said, even you have problem with the mathematician, mathematical manipulation, but please remember this graph. So atom, like human being, because we are solid, right? We are the solid one. Atom beam, so we prefer to go from the mountain to the land to the valley. But vacancy is the opposite. Vacancy is going to move from the valley to the land to the mountain. Okay, why this is important? So far, remember this. So far, if you can't understand any other things, but please remember these illustrations here. So please remember this illustration here. It's good enough for you to move on. Okay, so we move on now. We move on now. Okay. Okay, so this is the most important slide. Can you just really highlight this slide? So this is the most important slides. Okay, so now, what is sintering? So we said sintering, right? Sintering, you have two particles come together. So this particle 1 and the particle 2, particle A and the particle 2. So when the particle A and the particle 2, when they come together, so now let's see how the atom move, So I'm asking you a very quick question first. So from this graph, right, you tell me we have two sides, A side and the B side and the C side. Okay, so now you tell me, so which side is flat? ABC. Can you type the flat? Thank you. Thank you, Jason. Thank you, everyone. Very good, very good. C side is the left one. So which one is convex? Okay, you have already know that C is a land. So how about now we have a convex and concave. So which one is convex? Convex, A or B? A or B? Which one is convex? Convex is the one you're very familiar, like balloon, right? Balloon case. Okay, A or B? B. Yeah, A is actually a convex, right? A is a convex. Okay, but B here, okay, this one is actually, it's what we call is concave. Concave. Okay, so can you write down now? So the A side is actually a convex, and the B side is actually a concave. And the B side, we normally give them a name like a neck. Okay, then C side, it's actually a land. So C side, we have another name, which is grain boundary. Grain boundary. Okay, thank you all of you. You're following me, I'm very happy. Okay, so A, B, C. So you already put it down here. So the B side is the neck area, and the C side is actually the land area. Okay, so now we are very comfortable because we have already learned this Jansen's equation. We know how atom will move, right? So atom will move to where? Tell me. Atom will move to A, to B, or to C. All the atoms will move to A, to B, or C. Thank you, so good. You're very good. Which part of the A and B side are referring to? Okay, so A is just a particles. So this is you have a particle coming, right? You have two particles coming. Okay, so these two particles, so everywhere is A. All this because it's a positive radius, right? Positive radius. Am I correct? So this is everywhere is A. All these are A. All these are A. Everywhere is A. Okay, but now the thing is when you come together, so you're going to form this very special symbol, what we call is a neck. This is a neck area, neck area. So the neck area is B. Neck area is B, is a concave. Okay. Okay, very good. So actually all the atoms will move to the neck area. Okay, excellent, excellent. Okay, so now let's see, we have different ways for the atom movement. So we keep saying, what is centering? Centering is in the end, how the atom move from where to where. Okay, so how can we decide where the atom move? Atom is always move from the higher energy side to the lower energy side. Okay, so for example, now let's see. So for the first one, P1, what we call is an evaporation condensation, because sintering happened at a high temperature, right? So high temperature, some of the particles is already evaporated in the phase, in the vapor phase. So now they're going to come down to where? Again, where is the lowest energy site? It's supposed to be this negative, right? This is a neck area, because the neck area, can you write it down at this moment? Neck actually is equals to concave. Okay, neck equals to concave. Okay, so it's going to stay at the concave place, our neck. Okay, so this is the first one, evaporation, condensation. And also the atom is also going to move, right? So atom here is going to move from where to where? Tell me. This is surface diffusion. Again, from where to where? From A to B or B to A? Again, must be from, this is a simple question, everyone answer. A to B, good, good, very good, very nice, very nice, okay. So surface diffusion, which means atom is going to move from this surface to the neck, This is surface diffusion, okay. And also there's another possibility which requires a volume diffusion, which means it's still from the convex to concave, still like this, but they don't move from the surface now, they move from below the surface. So that's why we say it's a volume diffusion. Volume diffusion, which means your path is under the underground, which means it's not on the surface anymore. It's under. Okay, so from the surface to the neck, Okay, so that is a P3. So the P1, P2, P3 all tells you that atoms is going to move from the convex to the concave. Okay, so that is P1, P2, P3. But now can you imagine if my two particles come together, right? So in order for them to get rid of all the pores outside, or vacancies outside, right? So where is the contacting point for these two particles? Tell me, can you type? Where is the contacting point of these two particles? So good, very good. Yeah, green boundary, very good. So in order for you to have anything like a solid swapping of the atoms and vacancies, actually the real contacting point for particle A and particle B is actually the green boundary. Okay, can you write down here? So let me just, because it's been messy here now, just remove it. So the most important thing here, because where they are in contacting, you have A and B coming together particles. The thing is that forming is a green boundary. So this is the most important thing here. So the green boundary. So now I'm asking you a question now. So where the atom in the green boundary move from the green boundary to the neck, or from the neck to the green boundary? Atoms move from the green boundary to the neck, or neck to the green boundary? Atom. Very good. All of you answer green boundary to the neck. Very good. Green boundary to the neck. Okay. So the green boundary diffuse from the green boundary to the neck area. Okay. So this is P4. P4 and the P5. P4 and P5, the only difference is just you're either along this green boundary or below it. So that's every time when we talk about the volume diffusion, which means you're not diffused just along the line on the surface, but it's below, underground, okay, movement, okay. So this P4 and the P5, because these two happens at the green boundary, you always need to remember here, okay. We said before, in order for densification, you better to have densification first at where? Remember? You quickly form a green boundary, right? if you go back to our question before, so root 1 and root 2. So root 1 and root 2. For the root 1, you always quickly form a dense green boundary first. So which means in order for you to have densification, let's just form this very dense green boundary first. Okay, dense green boundary first. So in order for you to have dense green boundaries, so now you need to involve this vacancy movement. Okay, so far you're very happy, already know that the atoms is going to move from the green boundary to the neck. Correct, right? Green boundary to the neck, either along the green boundary or below the green boundary, which is fine. Okay, so there's a super important concept here. So this one is actually not required, but just help you to understand what is densification. So can you just follow me to read through the viscous or quick flow, the mechanism, either the plastic deformation or viscous flow of a particle from area of high stress, which is compressive, to the low stress, which is tensile. This is going to lead to densification. Okay, no worry, we just read through. This one is not required. Okay, but let's see this graph. Okay, so for example, so I have vacancy here, vacancy here. So first of all, this side is tensile or compressive. Tell me, tensile, compressive. You pull up. So it's tensile or compressive. Can you type T or C? Yeah, T are tensile, right? So then if this side is T, so which means this side is C, compressive, right? So then I'm asking you, which side is going to have more vacancies? Is tensile side or is compressive side? Which part is going to have more vacancies? Which part? Yes, very good, very good. Yeah, anything if it's volume, which means it's under. It's not on the surface, it's under. Okay, you can see the sign, you can see this it's a curved one. Okay, so the vacancy is actually higher at the tensile side, right? Tensile side. Okay, so you can see the vacancy is moved from where to where? From T to C or C to T. Can you type? Vacancy moved from T to C or C to T. Tensile side to compressive side. Okay, excellent. T to C are very good. Vacancy move from the higher concentration to the lower concentration. So vacancy move this way, and also because we have a compressive, which means your atom is actually moved from where to where? Atom move from where to where? Atom is going to move from C to T or T to C. Yes, very good, very good. Very good. So atom is moved for the opposite direction, right? So which means now you can imagine if my vacancy move this way, and my atom is a solid one, move this way. So what will happen? Tell me. If vacancy move this way, and my atom move this way. Okay, what will happen? Tell me. So this atom is going to separate. Actually, the atom is going to fail the vacancies. Am I correct? So actually, the atom, because they move to the opposite direction, so this one is going to fill the vacancies when they meet. Okay. So this one means what? Which means this one is called what? Your vacancy has been filled by my atoms. It is what? Tell me. Can you write the keywords here? The vacancy. You have a vacancy. Vacancy is empty one, right? Now it's filled by my atoms. So this one is what? This one is D E N S and densification. Excellent, excellent, Odelia and Sean. Okay, so it's densification. So which means what? Which means if you want densification happen, please make sure you have atom and vacancy move to the opposite direction, because only by doing so, your vacancies is going to be filled by the atoms and the vacancy will be get rid of. The densification means what? Densification means you need to get rid of the vacancies. Am I correct? So the only way to get rid of vacancies is to make sure you have atoms come all the way to fill it, to become a densification. So that is the concept here. So if we go back, that's what happened in this 5 and 4 and 5, P4 and P5. Okay, so of course now we have P1, P2, P3, P4, P5. So at any time, so this one is also very important claim here. At any time, any temperature, the farthest mechanism were dominant, which means what? Actually, in centering P1, P2, P3, P4, and the P5, all are going to happen. Okay, all of them are going to happen. So they're actually competing with each other. But which one will win? Is the farthest mechanism will win. Okay, so there's a one which you run faster, so it's going to win. Okay, so remember this one in this moment. Okay, so let's continue. Okay, now you can see because of this, right, we can see there, we can say there. So when you have an opposite flow of the atom frequencies, you will form these densified structures. So let's continue. Okay, this one is also not required. But as I said, I found this picture is easy for you to understand. So I use this one for you to understand the concept. So now what we put here, so the surface particle will go to the neck area. Neck area is the negative one, right? So this, when you have P1, P2, P3, all means that your okay. Just skip by yourself. Where's the recording? Oh, so sorry. I mean, I really can use all this as Google because we're not supposed to change computer every 3 years. So this is 2nd year. Oh. Anyway, so okay. So now let's see. So we just learned P1, P2, P3, right? So P1, P2, P3 is everything is going from the surface to the neck, or either you use volume diffusion. Okay, so this one actually does not allow the atom move closer. So simply just coupling, which means it's going to only become bigger and bigger and bigger. Because if you still go back to root 1 and root 2, so root 1 and root 2, the most important thing for root 1 to happen is you need to form a dense green boundary first. Okay, so that's the most important thing. You need to form a dense green boundary first. Okay, that's the requirement for densification. So P1, P2, P3 is actually only give you bigger ones. Okay, so that's P1 is evaporation, condensation, surface distribution is P2, and lattice diffusion. Okay, some people use volume diffusion, some people use lattice diffusion, some people use bulk diffusion. Because if you read book or read papers, different people use different names, but they're all talking about the same thing, which means all the atoms not move through the surface, but move below underground. Okay, now lattice diffusion from the surface to the neck. No matter what, it's always go to the neck, because neck is the negative, it's a concave case. Okay, so in this case, you're going to rose in the neck size, and there's no densifications. So we have actually learned this one before, what we call auto-rappelling. So the small grains will tend to evaporate away and plate up on the larger particles. So that is what we have seen before, right? So we have learned this because auto-rappelling. So basically, this is Young's equation, and we know that in chemical thermodynamically, the atom with larger mu is going to escape to where the mu is smaller. So simply the atom inside here is going to trend towards this side, become even bigger one. In the end, it will merge into an even bigger particles. So that's the end thing. So which means become bigger, which means coupling. Okay. So for densification happen, crystallization happen. Okay, you must have something happen at the grain boundary. This is highlight this one. Can you please highlight it? Okay, this is very important. We have to make sure the materials in the grain boundaries to have some densification. But then what is densification? We said before, right? In order for densification happen, the vacancy need to be filled by the atoms. Am I correct to say so? Right? So we have seen before. So that illustration to help us that. So evaporation, surface diffusion, evaporation, condensation is P1. Okay, so this one is P1, evaporation, condensation, P1. P2 is surface diffusion. P3 is lattice diffusion. Okay, you go back to refer to the illustrations there. Okay, so Thank you. So let's continue. Okay, so materials in green boundary. Okay, so now let's see what happens in P4 and P5. Now let's see what happens in P5. I'm asking question now. Can you start to answer? Okay, so first of all, my question, atomically, you have a green boundary here, green boundary. This is neck. Okay, so where are you going to have a higher vacancy concentration? It is a green boundary or it's neck? Can you type? Which side have higher vacancy concentration? It is green boundary or the neck? Hey, question. You answer. You listen to the question now. The question is now. Can you type that question? Okay. Atomically, which side you are going to have a higher vacancy concentration? Higher. I'm talking about higher vacancy concentration. It's going to be the neck or the green boundary. Neck or green boundary. Yellow. Yeah, concave. Correct, right? Correct. Okay. Correct answer. Okay. Good. Actually, it's the neck or green boundary is supposed to be the neck, right? Actually, also easy to understand because neck you have nothing here, right? Green boundary you have something already. So obviously the neck will have more pores or more vacancies. Okay. So neck and the other thing is because it's concave. Right, it's a concave case, a concave neck. Okay, very good. Okay, so in this case, so the vacancy is going to move from where to where? Is the neck to the green boundary or the green boundary to the neck? Can you type? Vacancy is going to move from the neck to the green boundary or green boundary to the neck. Okay, I received 2 answers so far, neck to green boundary. Okay, so seems you all reach the same conclusion. Excellent. Okay, so always remember this graph. So the vacancy is going to move from the neck to the green boundaries. Correct. Okay. So how about atom? So atom move from the neck to the green boundary or green boundary to the neck. I'm asking the atom now. So atom is moved from the green boundary to the neck. Excellent. So which means they are moving to the opposite direction or the same direction. Opposite or same? Can you type? Excellent, thank you. Opposite. Okay, very good. So that's what we put here. The vacancy move from the neck to the green boundary, and atom move from the green boundary to the neck. Okay, and since this is the movement, so obviously this movement during this P4 and P5, so the vacancy and the atom move to the opposite directions. So okay, so first of all, P4 and P5 happen at the green boundary already, right? So that fulfill the condition because we said in order to have root 1, you need to have a dense green boundary first. Okay, so first of all, it happened at the green boundary. The second one is because there's an opposite flow of the atoms and the vacancies. Okay, so which means densification is going to happen, yes or no? Is densification going to happen? Can you type? Yes or no? Yes or no? Okay, Sean Peck said yes. So can I receive more answers? Okay, Tan also say yes. Okay, very good. So you can see simply in this P4 and the P5. So number 1, it happened at the green boundary, correct, right? And number 2, the atoms and the vacancies move to the opposite directions because of the R is different, right? The radius is different. One is a fat one is the concave case. So in this case, we said, okay, that's why P4 and P5 gives you the densification. Okay, so this is super important. P1, 2, 3 give you coarsening. Coarsening is which root? Can you type? Coarsening which root? Coarsening. J, is it 1? J, can you? I'm talking, yeah, thank you. Yeah. Coarsening is 2, okay? So P4 and the P5 is root what? P4 and P5, I'm asking you now, next question. P4 and P5 is root. P4 and P5 is root 1, correct? Thank you, Sean. Thank you. Okay, P4 and P5 then is root 1. Okay, so that's now, can you have the overall picture already? So we learned last week saying, hey, if you want densification, P is trying to go to root 1. Because root 1, what happened first? You form a dense green boundary first. Okay, that's very important. Okay, then starting from this week, we know that all this Young's equation, blah, 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 we learned so many derived, so many equations. But actually, all just tell you a very simple thing is this graph. This graph, okay? Atom move from the concave, atom move from the convex to lambda to concave, right? Okay, and the vacancy move opposite way. And also then we know P4 and P5, so the vacancy is going to move from the neck to the green boundary, and the atom move from the green boundary to the neck. Okay, so simply, so then you will know that in P4 and P5, to fulfill these two conditions, so you will have densification. Okay, so this is super, super important. You can also have a look here. So I show you the graph. See, always happen at the green boundary, trying to densify first. Okay, always happen here. Okay, so that's the most important thing. Okay, remember the conclusion so far. Okay, yes, diffusion. Yeah, atoms move from the surface to the neck. Correct. P1, P2, P3. All it's not only this one, right? You have P1. You're talking about P2, but also P1 and P3 also give this coarsening. Okay. So so far okay. So now my next question. Question again. Okay. So a compact with a faster surface diffusion from surface diffusion. Okay, the surface diffusion happen faster than the green boundary diffusion happen faster. Will lead to densification or coarsening. Can you type your answer? Of the compact, which means a sintering with a faster surface diffusion. Surface diffusion is P what? Surface diffusion is P. Yeah, it's going to surface diffusion is P2, right? Surface diffusion is P2. So green boundary diffusion is P what? Green boundary is P. Green boundary diffusion is P4, right? So if now let's say if P2 is faster, so this whole thing is going to lead to coarsening or lead to densification. Can you write your answer here? Very good, Odela. Thank you. Coarsening. Thank you, Yongjing and Qingrong. Okay, so this one is going to have a coarsening. Answer will be coarsening. Now my next question. Okay, so I typed down. So this one is going to win. Okay, because this is P2. This is P4. Now I'm asking you, which one do you think need higher temperature? It is surface diffusion, or green boundary diffusion, or bulk diffusion? Which one need higher temperature? Okay, which one need the lowest temperature? Lowest temperature, which means it's easier to move. Easier to move. Yeah, exactly. Exactly, very good. So surface diffusion actually need the lowest energy, right? Because you just need move on the surface, right? So this one is a surface. This is surface, okay? Surface. And the green boundary, green boundary diffusion, green boundary, although it is like you have a green boundary, right? Green boundary here. So although you have solids already, but you still have some vacancies to move, right? Because green boundary, you know, is a defect, full of defects, full of vacancies. So you still have ways to move. So bulk diffusion is the most difficult one. Bulk diffusion is here. So this is surface diffusion. This is green boundary diffusion. This is bulk diffusion. Okay, bulk diffusion. Okay, surface is the easiest one. Now, bulk diffusion is the most difficult one. So now I'm asking you, if you want P4 wing, you want higher temperature or lower temperature? Can you type? Excellent, excellent. Yongjing and Jay both answer high. Correct, right? Correct, right? Right, that's what we said before, because green boundary diffusion will be much more difficult compared with surface diffusion, because surface diffusion only make everything become bigger and bigger and bigger, correct, right? So we need a green boundary, P4 and P5, to make sure the everything happen at the green boundary, and also make sure you will have the densification. So that is why, explain why we need higher temperature to get higher densification. Remember, what is the ultimate goal? Can you write down the ultimate goal now? What is the ultimate goal for sintering? What is the ultimate goal for sintering? The ultimate goal is trying to get the theoretic density at lowest temperature. Excellent. Thank you, Yongjing. Thank you. Excellent. Okay, so achieve highest density at lowest temperature. Okay, why is so? It's because you know in order to have densification, you need to make sure P4 and P5 to happen. But P4 and P5 need higher energy, right? Because need higher temperature compared with P1, P2. Okay, surface diffusion. Okay, okay, so that's what we put here. This is grain boundary and this is surface. This one need higher energy compared with surface. Okay, so that is all. Okay, so we can summarize so far. Okay, quickly, coarsening and densification, which happen faster. Maybe this one we don't have time to explain. You can read through by yourself. There's a different stage, initial stage, intermediate stage, and final stage, which means you have 3 stages. So now we need to know which is faster. So as we said before, P1 to P5, all is going to happen at the same time. At any stage, any time, everything is going to happen. But which one is winning is the one which is going to be the dominant one. Yeah, you ask a very good question. Okay, so there will be an increase in surface diffusion, right? So not necessarily. It's just the surface diffusion, you need lower temperature to happen. Okay, but P4 and P5, you need higher temperature to happen. Okay, so as I said, P1, 2, 3, 4, 5 happen at all the time. So that's why we need to calculate its rate. Okay, I'm not saying the P4 and P5, when P4 and P5 happen, P1 is not happening. Actually, everything is happening at the same time. P1, P2, P3, P4, P5 happening at the same time. Okay, but the thing is, which one is going to win? You need to calculate the rate. Okay, so that is what we have. This is example, this is initial stage, intermediate stage, final stage. You can read through by yourself. Since I said this is not required, but you just know there's 3 stages in sintering, 3 stages in sintering. Okay, so then move to this question. Okay, so this definitely is not, I'm also teach this one for postgraduate. Okay, so for postgraduate, all these calculations are required, but for undergraduate, I'm not requiring you. Okay, so as I just said, so P1, 2, 3, 4, and 5 happen at any time. It's also going to happen. It's just more or less which one is faster. So that's why in each of stage, so we just said we have 3 stages, right? Actually, in 3 stages, all of them is going to happen. Okay, so in each stage, you have to calculate which one have the higher rate. So this is one of the P1. So we have a calculation here. So get the P1, the rate, the net growth rate is going to be something like this, but it's not required. We also have like we calculate P5 here. So then we can calculate which one is faster. Okay, so this is actually a lot of fundamentals there. So then we know, oh, because then if we compare that at certain temperature, at certain time, so P5 is winning, have a faster rate. So we say in this case, you're going to have more densification, less coarsening. Okay, so that's the essence behind it. So everything is about competing, okay. And also we have P4 and P2. So all these have equations, but it's not required. And also the viscous like sinterings and also not required, but some general remarks. So you can see it's very complicated, right? It's very, very complicated. Okay, so the fundamental behind, let me summarize again, okay? So P1, 2, 3 give coarsening, P4, P5 gives densification, and P1 to P5 actually happen anytime. Okay, so can happen all the time. But the thing is, at certain time or certain temperature, some is going to win. Okay, so that one will be more predominating. So if you go back what we learned before, like root 1 and root 2, root 1 and root 2 actually always happen at the same time. But you just need control. For example, if you want more densification, please make sure the root 1 happens more. If you want polar structures, you make the root 2 happens more. Okay, so there's some like a general remark. So it's actually very, very complicated. Very, very complicated. If you really want to get all these details, you need to know how to calculate all this. We call it a rate. So which rate is faster is going to be dominated. Okay, but we skip all this mathematics here. So there's some like general remarks. So the activation energy is the lowest for surface. That's what we said before. Lowest, the surface is easiest one to happen. Surface is easy one. Grain boundary is a little bit more difficult, but lattice diffusion is the most difficult one. So in order, okay, the surface That's why in order for surface diffusion to happen, you need lower temperature. Okay, that's why if you sinter at very low temperature, so most likely we'll have surface diffusion, which is P2. So for this P2, most likely we'll get crystalline. So that's why lower temperature, you won't get very densified structures. Okay, and also this is some general remarks. So smaller particles, so in this case, grain boundary and surface diffusion are preferred over lattice. So you can say all could be different. On longer sintering time, high sintering temperature, and larger particles, so lattice diffusion is going to be favored. So these are some general remarks according to all these calculations. Okay, so let's continue. Okay, so skip. So this is an example. So I share with you. So you can see I'm asking you. So the densification, what is the rate? The rate controlling mechanism, if it's a lattice or it's viscous flow. So you need to calculate which one is faster. So whichever one is faster, then it's going to win. Okay, but the details is not included. So the most important thing is we understand the fundamentals behind it. Okay. So again, this is not required. Okay, so summaries. So actually this summary is supposed to be at your page 53. Can you look for your page 53? Yeah, so now let's quickly write down the summary so far. Sintering, the driving force, reduce the surface energy via either P2 or the root 2, crystalline, and root 1, which is densification. Okay, and also Young's equation, Kelvin equation tells you the atoms move from the convex to flat to concave, but vacancies move to the opposite. Okay, and this is Young's equation and Kelvin equation. And also we learned 5 atomic mechanisms. So we know the P1, which is evaporation, condensation, atom condense from vapor at the neck. Okay, surface diffusion, which atom move from the surface to the neck. Okay, volume diffusion, which means atom move below the surface to the neck. So everywhere it's going to the neck. Okay, and also we said densification. So densification happens. So everything have to happen at the grain boundary because that's root 1, right? We need to form a dense grain boundary first. Okay, and also at the same time, the vacancies and atom need move to the opposite directions. So that is P4 and P5. So in P4 and P5, because everything happen at the grain boundaries, so grain boundary diffusion atom again move along these grain boundaries to the neck, or atom below the grain boundary to the neck. Okay, again, the source is still the neck because the neck is a concave. So this is summary so far. Okay, so you can take a screen print here. Okay, so let's continue. So I give you some like factors affecting the solid state sinterings, because this could be some like a common sense for you when you do your FYP. Okay, so that's what we said here already. So temperature, right? Temperature is a very, very important factor here. So temperature, since diffusion is responsible for the sintering, because everything is about how the atom move, how fast the atom move from where to where. Okay, so in general, if you have a higher temperature, you are going to have a higher sintering kinetics, right? So higher temperature, which means no matter what atom, even below like a bulk diffusion could even happen. Okay, so that's what we put here. The activation energy for bulk diffusion is actually larger than the surface and the grain boundary. The surface is the easiest one, and the bulk is the most difficult one. Okay, so in order to have densifications, please make sure your temperature is high enough. Okay, and also there's some general things. If you want good densities, so make sure you have a grain density. So you still remember what is grain? I'm testing you now. What is grain? I used a word before to help you to remember. So remember what is the process, solid state reaction? Yes, very good. Before sintering, like a papaya, like green papaya, which means not ripened yet. Okay, so what is sintering? Basically, you mix powder, you mix together, ball milling, right? Then sieve, then form a shape. Remember, form a shape. So that one we call it a grain shape. That grain shape, which means before sintering. Thank you very much, Yongjin. Thank you. Before sintering. Okay, so obviously, if you have less pores to reduce, so it will be much easier for you to sinter more densified structures later, right? So in order to have some like a better solidification or densification later, please have higher grain density. So higher grain density is going to, later you're going to have less volume of porous to reduce. Okay, and this number 3, the uniformity of green microstructures. Okay, remember, it's always better if you start with some like more uniform structures instead of something like this. Okay, actually you can also understand this one, A and B, which one is more dense, A or B? Which one is more dense? Is A or B? Yeah, it is always A, right? A, because it's, so you can always imagine like a green. So these two are roughly actually the same thing, okay? So normally you have a little bit more uniform structures, you will also have a better green densities, okay? Which means you're starting with much less pores. Okay, you have much less pores to reduce later, because in the end, sintering is about reduce all the pores, okay, make it densified. Okay, so so the uniformity of the green microstructures is very important. So reduce the agglomeration, because like in this case you have a lot of agglomerates, means become very big particles or like agglomerations. Okay, so for example, I give you an example here, so you can see. So if you have two things, so this one, this dot is an agglomerate-free powders. Agglomerate-free powders, okay, which means you do something, make the powder not aggregate together, so you will in the end have a bit higher density. Okay, so how can we reduce agglomeration? If you still remember, we can use what to reduce agglomeration? Like a ball milling, right? Ball milling, and also you can use sieving. You can sieve to reduce this different size. Maybe the big particles is going to stay and sieved away. Okay, so these are the agglomeration free. Then you can get better density later. Okay, and the atmosphere we don't have time to explain, so just skip. Okay, so I just put, because, and also atmosphere is case by case studies. Some case it helps, some case does not. Okay, so this one I use more or less like reference things for you if you're dealing with your FYP or your PhD, you're dealing with sintering. So you can always refer back to these notes for you to find whatever you need to explain your results. Okay, because for atmosphere, so it's more or less as I said. So for this 1, 2, 3, it is more general. It occurs for almost everything. But fourth case, atmosphere, something could help, something will worsen the scenarios to make it even more porous. Okay, so I skip it. Okay, so and then the fifth one, the size distribution. Size distribution, again, this is a little bit like a number 3, so which means it's better you have a uniform thing first. It's also, it's very easy to understand, right? If you want more dense, more uniform structures, you start with more dense and more uniform structures, right? Your green structures need to be more uniform. Your powders need to be start with more uniform, same size, instead of one particle is very big, one particle is very small. You know what I'm trying to say, right? So the size distribution, if you have a narrow grain size distribution, will decrease the propensity for abnormal grain growth. So for example, for this case, right, maybe you start your particles at the very beginning roughly the same. But for this case, maybe your some particle like this, some particle is like this, some particle is like this. So everywhere is different. So in the end, you will have some very odd, we call it abnormal grain growth. Okay, so again, is the principle behind it is also more common sense, right? If you want uniform, dense structure after sintering, so please prepare your everything before sintering is more uniform, more dense. Okay, so that is number 5. And then number 6, I think we skip this. Also is case by case study. We only explain this number 3. Okay, so suppress the grain growth and lower the grain boundary mobilities. So why this is important? Remember root 1 and root 2. Root 1, root 2. Okay, so if you remember root 1 very clearly, so please answer my question now. If you want densification, you want grain growth happen earlier or later? If you want densification, that is root 1, right? So you want the densification to occur, so you want the grain growth to happen earlier or later. Is later stage or early stage? Excellent, later stage. Grain growth happen later. You always quickly densify the grain first, form a very dense grain boundary first. Then later you can relax and become grain growth. Okay, so this will help you to have a very good density instead of at the very beginning become very big. That's cosmic. Correct, right? So for example, I'm giving you one example here. So let's try to suppress the grain growth. Suppress the grain growth. How can we suppress grain growth? We add some impurities. Okay, so for example, I give you one example here. So you can see, so this one, which means you don't have any impurities. Impurities are this one, the dotted one is without impurities. Okay, so this is a numina. Okay, but if I add a little bit magnesium here, means I give them a little bit of magnesium here, will make a huge difference. So you can see the grain growth will be slower, right? Compared with this one grow faster, but this one slower. What's the good thing of slower? Is because once it becomes slower, so then when later you will form more densified structures. Okay, so that is the good thing of these impurities. Student questions. Yeah. Okay. So for example, so remember here we said, okay, if you really want this, I was saying this before, I just help you review. If you really want more densification, make sure you go to this. This is extreme case for root 1. So let the grain growth happen later better. So how can we make this one happen later? We give some impurities, and ask this impurities stay at the grain boundaries and stop the grain boundaries become bigger to become a bigger grains. Okay, so actually there's a science paper, in 2006. You know science? Okay, you know the NTU professor, you know, if they can publish a science or Nature. These two journals means that the top international scientists in the whole world. I think in NTU maybe only 2 or 3 professors can publish a science or Nature in their lifetime. So it's a very it's the top possible research articles in the world. Okay, so this is one example I'm sharing with you. So you can see this again is a numina. It's a numina. Okay, so it's a numina. Okay, so with this one, right, you can see. So this is one grain. Grain means what? This is atom, right? Atom. Okay, atom. So the atom is here. So the grain on this side, which is this one. So then on the other side is this one. So what is in between here? Tell me. Can you write down the name here? What's in between here? Can you write down? No. Yeah, grain boundary. Excellent. Grain boundary. So the grain boundary. This is grain boundary. So what is grain boundary? So you have one grain. So the crystal orientation is like this. You have another grain. You have the crystal orientation is like this. So in between is grain boundary. So grain boundaries obviously have more pores and more defects, right? Okay. So now I'm asking you. So if now I have impurities, so will these impurities go to A place or go to B place? A or B? Right, you always go to B, right? It's empty, it's more empty, so it's easy to go in, right? So that is why, so these scientists, they find that if they dope the alumina with etcher here, I think in this case, the etcher here, and they use this TEM to can see, hey, etcher is actually really here. It's here, okay? So this is a grain, this is another grain. Okay, so then this is good, right? Because if you want this hosen become a bigger grain, so in the end, I give them a lot of time, like heating up. So after some time, so all these grains, they're not tilted anymore. They're not like tilted anymore. They actually will become the same direction. Okay, so that's become a grain growth. Grain growth means in the end, for this one, right, you will merge as an even bigger grains. Maybe the final grain, this grain orientation is something you only have one orientation in one grain, okay? But now you can imagine if I put some stringers here, some stringers in the middle. So do you think it will be more difficult for the grain to become an even bigger grain one, or more difficult? Easier or harder? Easier or harder? If you put impurities in the grain boundaries. So do you think will be easier to form this structure or harder? Excellent. Thank you, Jinto. Thank you, Jinto. Yeah, correct, right? So that's the thing. So if you can have dope some impurities, and these impurities will stay in the grain boundaries to prevent the grain boundary, to prevent the two grains before they're tilted, right? You prevent them to come merge to become even one grain. Okay, so that is the impurities effects in this case. doping increase the grain size distribution. No, this is, okay, doping is just very, very little. Every time when we talk about doping, it's very, very little. Okay, so it's just like atomic percentage. So it won't affect the grain size. It's just at later stage, okay, so it will help, just as we said here, right? So more or less like just, you will still have grain growth, but just at later stage. Okay, I'm not saying you cannot have grain growth anymore. It just will not happen later, as some student already answered me. Okay, so this is another one. All the rest, because we don't have time, so we don't explain. Okay, so please mark where. Okay, so the particle size, again, is case by case thing. Okay, the larger initial surface, of course, you have a greater driving force, right? Because we calculated before, right? Smaller particles have much larger surface energy, correct, right? So you start with smaller one, you will have a greater driving force to get centered. But the problem is, once the particle become too small, it's actually very easy for this small come agglomerate together. So later they're going to center into bigger particles. So good and bad, again, it's about balance. Okay, so in principle good, but in practice may have problems because too small particles, you might have agglomerations. Okay, so summary. So you just have learned this. We have write down already, right? Okay, so this is 1, 2, 3, very, very important, especially this one, very important. Actually, all important, very important. Okay, so we come to some like general tools. Okay, so the higher temperature normally give you a bit higher, is help to promote the bulk diffusion and the grain boundary diffusion. I mean, in general, it's going to enhance these densifications. Okay, and also we said if you have better densification, give them a higher grain density and higher uniformity and the lack of agglomerations, right? We have already explained. No matter what, you want to dense things later, make sure you're starting things more dense, more uniform, and no agglomerations. And the impurities, certain impurities can suppress coarsening and the grain growth and lower the grain boundary mobilities. Okay, so you have foreigners, but just gut the grain boundaries, make this one more difficult to become merged as an even one. And then this one not needed. Okay, the gas dissolved solid to reduce pores and larger particle distribution will promote the this one we learned, right? So you cannot have too large, like one particle is 1 micron, the other particle is 10 nanometer, then you will have a disaster. Okay, it's better roughly everything is the same, or like 500 nanometers roughly, then most likely we'll have more uniform and dense structures. Okay, so that's the summary. So we just don't need this one, we did not explain. Okay. That's summaries. Okay, so we have about 20 minutes. So let's move to the last one. The liquid phase sintering. So liquid phase sintering we said before, right? So basically you have again you have impurities here. The impurities here, this is impurity B, A is here. Okay, so again you just put a little bit of a B here, impurities here, and most likely this B normally have a lower melting point. So which means when you reach certain temperature, right? So A is not melted yet, right? It's still solid, but the B become a liquid already. Okay, so that is a very important thing. Okay, so actually this liquid have very good commercial importance because it's rapid and it's uniform densification. Okay, so let's explain why this is the conclusion here. Okay, and also we said the solid result in the formation of liquid because this B become a liquid now. So liquid need to have a appreciable solubility of the solid phase. We'll explain this one later. So now you can see so before if it's solid centering, right? Solid centering. So what is this gamma? Tell me. It's gamma what? This is S, right? S what? Gamma SV, right? Gamma SV, right? Because outside is vapor, right? Gamma SV. But now you tell me the change to what? Because it's not vapor anymore. It's not vapor anymore. Okay, become liquid. Very good. Okay, so that's what we put here. Okay, so the surface energy considerations are, so now you have solid. This is your particle, right? This is your particle. So now you have a liquid. Now you have a liquid. So this liquid form a liquid. So this liquid is going to have a wetting angle. So have you learned wetting before? Can you let me know a little bit of your background? Because I understand some people told me they learned, some people said they haven't learned. Have you learned wetting before? Because if you learn, then I will a bit in 2016. A bit, okay. Then maybe I just very, very quickly, okay, give you some very basic understanding. Okay, so first of all, you see these two, right? So I give you extreme case, extreme case. So for example, we said, okay, this one is a gamma SV, right? We just explained already. For this case, extreme case, extreme case. So this one is a liquid. This one is liquid, and this one is solid. So this case is a wetting or non-wetting case. Can you type? You just instinctively think this one. If liquid is something like this, and the solid is someone like this. So this is a wetting or non-wetting. Excellent. Hey, which means you learn now. All of you learn already, right? All of you say non-wetting. Very good, right? So you learn already, right? Okay, correct, right? Non-wetting means what? Non-wetting means this liquid does not like this solid. So that's why the curl up, like a ball here, okay? Curl up, right? Sphere here. So you can see because there's not much in contacting. So it's non-wetting, just like you pour water on the ground, right? So the ground doesn't even have water, right? Because the water will curl up. Okay, so that is a non-wet. This is extreme case. So what did you see the angle here? You see the angle? Can you type? Do you see the angle? I assume all of you know already because all of you answer non-wetting. What is the angle here? Do you see the angle for this extreme case? Yeah, 180 degree. Okay, so you know everything already. So okay, so this is 180 case. So now you can imagine, right? Which means if theta is less than 90 degree, so we said it's wetting case. Wetting case, because if 90 degree, right? So you can see the liquid and the solid interface is something that's quite large. Liquid and solid interface, right? Which means this solid love this liquid. So that's why they have an interface in between. But if this one, the theta now is larger than 90 degree, so obviously you can see the interface is much shorter, right? Which means this liquid does not love this solid, so it's non-wetting. Okay, just like you pour water on the ground, it won't in contact. This water hits the solid, so it won't in contact with the ground. Okay, so it's curled up. Okay, so it's a non-wetting case. So theta angle is very important. Okay, so we continue. So now I found you answer all the question already so correctly. So I can move on. Okay, so this is obviously you can see all the water just curl up. Okay, so this is a non-wetting case, right? Very extreme non-wetting case. But this wetting is coming from the surface structures. Okay. Okay. So first of all, which one is wetting? So you have, for example, you have what is sintering? Sintering, you have particle A, solid 1, and solid 2, right? Solid 1, solid 2. Okay, so sintering is what? Sintering, which means you need to find a way quickly bring this solid 1 and solid 2 together, correct? That's densification, right? Remember, densification is what? Densification is you quickly form a green boundaries, which means let's find a way to help this solid 1, the particle 1 and particle 2 come quickly together. Okay, so that's the sintering. Okay, so now because we have a liquid in between now, liquid in between. This is liquid in between, and also liquid in between. Okay, this is also solid 1 and solid 2. Okay, so which case is wetting case? Wetting. So is A is wetting or C is wetting? So which is theta angle? So this is a theta angle. So yes, wetting is A, since you have the background already. So wetting is A, so C is non-wetting, right? C is non-wetting. So now let's see, if C is non-wetting, which means the theta angle is something like this. So now I'm asking you a very interesting question here. So since now this curve is something curved like this, So you have a curvature now, right? Remember, once you have a curvature, you will have a pressure difference, correct, right? Correct. So now I'm asking you the pressure inside here, P inside and P outside. Which one is higher? P inside and P outside, which one is higher? P1 inside is higher or P no is higher? Excellent. So this one is more or less like a balloon case, right? The balloon. So which means this R is larger than 0. So this P inside is actually larger than 0. Okay. So P, so which means your delta P now delta P is equals to P inside, P curvature. Some people use a P curvature, but I thought it's P inside is easier for you to understand, minus P outside. Okay, so in this case, if it's a non-wetting case, actually it's larger than 0. So now I'm asking you, so these two particles, S1 and S2, they're actually pushing away or pushing closer to each other. So away or closer. Because the pressure inside is larger now. Thank you so much, Yongjin, Jun To, Sean Pet, Eric, very good, Sean, Jin Shang, so good, so good. Okay, so in stage 1, push away. So now you tell me, so this is making more densified or less densified? More or less? Push away or push away? Less densified. Very good, right? So this gives us a very important concept, which is what? In order for this densification to happen faster, so let's try to put liquid in between. But the thing is, the liquid must be wetting your solid. So which is this case? So now you can see this is theta angle. How can you say it's a wetting or non-wetting? It's also there's another way, right? Like you see this interface compared with this interface. So obviously this liquid love this solid, right? Because they're trying to curve like this. So you have a bit more in contacting with the solid, okay? So I can get rid of it because it's a bit messy already. So now let's say this wetting case. We just now explained the non-wetting case, okay? So in this case, the theta actually is less than 0. Oh, sorry, less than 90 degree. This is a wetting case. So wetting theta is less than 90, okay? We ignore all these calculations, okay? Don't worry. As I said, you're undergraduate student. Okay, so now I'm asking you, you also have a P inside and the P outside. So in this case, because the shape changed now, the shape changed. Actually, in this course, we say it's a Seidel case. The Seidel case and also the R actually is less than 0. It's actually a concave case. It's less than 0. But anyway, ignore the details because we didn't learn it, okay? But there's a way to determine which side is higher, okay? So for example, if you have a paper, your paper is something like this. If your paper is flat, right, which means your pressure here, A and B, is supposed to be what? Okay, I draw 3 things. So this is pressure A and pressure B. Also this way. You just use some like instinct to understand this, okay? So for example, if it's a flat, if this paper is flat, there's no shape, no curvature, right? So PA and the PB, the pressure up and pressure low is supposed to be, PA is supposed to be same, equal. Thank you, you're so good, right? So PA is supposed to be equals to PB, right? But if you have this shape, so PA is supposed to be larger or less than PB in order to get some shape like this. Right, larger, right? Good. Okay, so if you want something like this, so PA is supposed to be larger or smaller than PB. So PA is supposed to be smaller than PB, right? Is it? Right, exactly. That's good, right? Okay, you can also use this when you help you understand, okay, if you're not comfortable with R thing, you know. So that's what we justify here, right? So you, for example, so inside here, normally if you want this shape, right, this shape. So obviously the pressure here inside is actually larger than the outside. So this is another way to understand, and it's easier for you to understand, okay? If you have problems, say, what is R is larger than Z? I really hate this convex and concave. I got really confused. So this is another way for you to understand. Okay, so for this case, so obviously, so since this one, if in mathematics, I ignore the mathematics here. In this case, this R actually is less than 0. So it's a concave case. Since a concave case, so the P inside and P outside. So in the wetting case, so P inside and the P outside. So which one is bigger now? You tell me. Which one is bigger? Can you type? Is P inside or P outside is bigger? Which one is bigger? Excellent. So P outside is actually bigger, right? So which is opposite to this long waiting case, correct? Okay, so that means good. That means what? So now you can imagine. So this two particle is going to come closer or move away. Come closer or move away. If theta is less than 90 degrees, because the pressure outside is actually bigger. Yes, very good, very good. Closer. So now I'm asking you, if I want densification, you want a theta is less than 90 degrees or larger than 90 degrees? Thank you so much. All of you understand already. I'm very happy. I'm very, very happy. Okay. So hopefully after all this, as I said, student at the very beginning, lousy, what is this? Like concave, convex? I got very confused. But as I said, if you learn more and more and more and more, you will understand much better as an overall pictures here. Okay. So as I said, so this is not required. All these equations not required. No worry. But let's continue. Let's continue. Okay. The whole thing of this picture here is in order to have densifications. So this force, this gamma force here, okay, this requires a capillary force. I think you also learn in other courses. There's a once you have a liquid, right? Once you have compared with solid centering, now you have a liquid phase. This liquid phase is going to give you very large capillary force, which is gamma LV here. Okay, gamma LV, liquid vapor, okay, gamma LV here. This capillary force, if theta, given the condition theta is less than 90 degrees, is going to give you a strong attractive force between the particles. Okay, so if you're combining with this lubricant liquid, so this capillary force is giving you a very rapid particle arrangement and densifications. So that is why liquid phase is helping the densification. Why is so? It's because this capillary force, this gamma LV. This gamma LV. Okay, this large capillary force induced by this liquid is going to, of course, theta less than 90 degrees. I always remember this condition. Okay, so it's going to give a very large attractive force. Attractive force. Attractive force means you're going to densify much faster. Okay, so that is the essence. Okay, continue on. So there's actually 3 stages during this liquid phase compared with centering, solid centering. Okay, so the very beginning is they have this particle arrangement, then followed by this solution precipitation, and the last one is skeleton centering. Okay, so what they have is the particle arrangement is densification happens under keywords. Can you highlight? Capillary force, and fill the pores by the liquid phase. This process rapid liquid flow and complete fill the final. So they can even reach 100, of course, a little bit exaggerated, but in most cases, compared with solid phase, because you have extra force pull the particle coming together faster. So this one will give you much higher densification compared with solid phase centering. Okay, and the second one, the second stage we call it a solution reprecipitation. Okay, so I think you will read all these things, like, because we didn't explain the equations, please just cross out. But how can you understand this whole thing? The solution of atom at the contact point and repetition away from the contact point. Actually, it's very simple, you know, because it's just because now if you have a particles and the particles in between, right? But in between you have liquid now. This is different from the solid phase. Sorry, this is liquid phase, right? You have a liquid in between now. So now you can see the atom here now. The atom here now, okay? So the dissolution of the atom at the contact point. Contact point is what? Contact point is what? I always said, what is contact point when you have 2 particles come together? Can you type? Green boundary, right? Keep up talking about green boundary, right? So green boundary, so the dissolution of atoms at the green boundary will re-precipitate away from the contact area. So it's just this contact point. So the atoms here will go to where? This again will go to the, since it's away from the green boundary, go to where? Tell me. You're moving away from the green boundary. You must go to where? Go to where? Tell me. You're always everything go to where? Tell me. Net. Wow, good, very good. You all of you very, very good. I'm very proud of you. Very good. Go to net. If you want to understand this thing, because all the notes prepared, we have to use textbook to help you, okay? But textbook sometimes write very strange words, okay? So help you to understand. So basic thing is at this stage, right? Once you come closer very fast already, you form a green boundary. So now the atom at this stage is going to move from the green boundary to the neck. Away from the green boundary means go to the neck, okay? And also there's another thing, okay? So the diffusivity in the liquid are orders of magnitude higher than in the solid. So also what does this mean, okay? So because we only have 5 more minutes, so I leave this one to explain in the tutorial. Is that okay? We leave this one, okay? So the last one is solid state sintering is just once everything forms, so the rest is just solid state take over. Okay, so this is the 3 stages of this liquid phase sintering. Okay, so you can see, so liquid phase, the very best thing of liquid phase is what? Can you type? Is the faster gasification, right? Because of the capillary force coming from where? Coming from the wetting liquid, correct, right? Okay, all these are important things. Okay, so in order for rapid gasifications, there are 4 conditions. So first of all, you have to have a appreciable solubility of solid in liquid to transfer materials. So obviously, right, so the atom need to move, right, through this liquid, right? Otherwise, it's all about how atom move, right? So atom move faster in the liquid, appreciable. So you have to get soluble in the liquid. The solid have to be insoluble in the liquid. Otherwise, it cannot move, right? So they need to have an appreciable solubility of a solid in the liquid to transfer materials. And also this one, since we did not explain, so you just remember the conclusion, which normally if you have a better, smaller particles, you will also have a larger capillary force. Larger capillary force, which means it can come closer faster. And of course, right, we said you need to have wetting. If it's not wetting, please make it even worse. And also make sure you have enough liquid to wet or overall the solid phase. Otherwise, somewhere you have liquid, somewhere you don't have, make the whole sintering is not uniform. Okay, so this is 4 conditions for rapid gasifications. Okay, so then we continue. So the problem is, okay, so far we said all the good things, right? Very, very good, very, very nice. Yeah. We love it. Okay, so that's what we say here. So liquid phase are more forgiving in terms of powder packing. It's faster. It is more economical than the solid state. So that's why in industry people use it very often because it's much easier to form gasification first. Okay, so I give you one example like this little troublemaker, silicon nitride, very difficult to gasify if we don't have any liquid phase there. But there's a problem. So my question here is, no matter what, so remember what is liquid phase sintering? You have A, you need to add a little bit of impurity B there, right? Correct? So now I'm asking you, where will this B go after sintering? Can you type? In the end, the B will not run away, right? It still will become solid somewhere. Will stay where? The B is impurities, right? It's the sintering aid, it's a liquid. So where will this B go? So liquid phase sintering, you have A, everywhere A is, you only have a little bit B here. B is become a liquid phase first. Yes, very good. We go to the green boundaries. So the green boundary, it is already very disordered already, right? Compared with greens, okay, it is already very disordered. But now you have foreigners there. So which means it's even worse. Okay, so in many applications, the presence of glassy films, which means very disordered green boundaries, because you have some foreigner that make even more disordered, so it can be very harmful. For example, I give you one example here. The creep resistance can be significantly compromised by presence of this glassy phase at the green boundaries, because this one is going to soften when you heat. When you're heating up, it's going to become softer, this green boundary. Okay, this is the first one. The second one is because this impurities is going to stay in the green boundaries, and this could be some like ionic conducting glass phase. Again, the green boundary is become more ionic conducting, so which is not tolerated in insulators, which means your green boundary become too conducting. So this is going to affect the electrical properties. So these are the 2 examples. So not everything, although the liquid phase is good, it helps with gasification, but no matter what, it is impurities. So in some applications, this impurities is so predominant, is a dominant factors to influence the properties. For example, creep resistance, for example, for the ceramic insulators. So that's why actually in electronic ceramics, people don't really use it very often, because in electronics, people hate impurities or really hate it. They want to control everything in a perfect way. Okay, so this one you can read through. So in order to have different properties, in the end we said, right, we talk about dense, porous, all the structures. Okay, so for example, if you want high strength, better you have a smaller grain size, uniform structures, no porosities, high toughness. Maybe this one you didn't learn. Actually, you're going to learn in week 4 and 5 at this moment. I mean, at least in CA3, I'm not required. CA2, I'm not requiring you. Okay, CA2 is not required. Okay, the high creep resistance, large grains, and also please have free of amorphous grain boundaries. Means please make sure your grain boundary is not that disordered. Now, optical transparency, later we're going to have pictures, and low dielectric loss, better this form, and catalytic. Oh, catalytic is very different. Catalytic application, you need actually very large surface area. Very large surface area equals to what? Tell me. Very large surface area means what? Can you type? Thank you so much, Sean Peck. Excellent. Which means actually, in almost all the other applications, you need dense structure, except this catalyst. Catalyst, you need very porous structure, actually, on the other hand. So everything is dependent on what you want. It's not, as I said, nothing is perfect. So it's all dependent on what you want. So you need control. Okay. So so lesson this one we did not include, just skip. Okay. So for example, you see all our alumina, in this case, all our alumina, but if you become a single crystal, so you can say it's very transparent. So if it's a polycrystalline, so the grain boundaries is going to scatter a lot of light away, so it can be translucent. But if you have a polycrystalline, at the same time, still have a lot of porosities. So this has become just completely opaque. So all this, you can say same materials, but if you control them with different microstructures, you will have completely different properties. Okay, so this is what you can see. Okay, so please screen print. Okay, so large capillary force by this wetting liquid, where wetting, can see this is the keywords, wetting, the capillary force is going to attract particle closer. This is going to enhance densification. This is the essence of the liquid sintering. And we have 3 stages, stage 1, stage 2, and stage 3. And also 4 conditions must be met in order to have good densifications in sintering, in liquid sintering. However, in many applications, the presence of this grain boundary is not wanted. And the last one, property is very much dependent on the microstructure. Okay, so this is all for the last section. So we have a tutorial to emphasize, to help you to understand more. And just now, sorry for the accident. Hopefully my computer won't black out again. If yes, you have to help me to talk to the chair and ask them to change my computer. Now I'm just joking. Sorry, a bit overrun a little bit because of the accident. Thank you, and stop recording.